Okay, so it should be rolling. And yeah, so I just gave you back the homeworks that you turned in on Monday of last week. The ones that you turned in on Friday, that were due just a couple of days ago, I should be able to give those back to you tomorrow night. So the only homework that you won't get back before the test is actually the one that you're going to turn in tomorrow. So if that bothers you, what you should do is take pictures of your homework so that you can keep it to study from, and then I'll post solutions after tomorrow night, so you guys will be up to date on that. So that is that. Again, there are a couple of videos to watch online if you're having trouble with either doing EROs to find determinants or with Cramers Rule. I also made a video since I didn't really cover it in the lecture. I do want you to know that stuff. It could be on the midterm. So speaking of the midterm, it's on Wednesday, and it will cover chapters 1, 2, and 3, pretty much up to what we've now covered. Most of tomorrow night will be moving on to new material. So I may say a few more wrap-up words of wisdom about these first 3 chapters, but most of the midterm stuff is ready to go. So you guys hopefully you can start working on the review packet, the sample test, and see how those things go. Let me give you a little bit of an idea of the breakdown for the test. So the midterm, and the midterm will be closed everything except I will give you that table of integrals that I gave you for the quiz, that exact same table. I'll give that to you again. You shouldn't need anything other than that table and some basic integration skills. So chapter 1 might be about, I put here about 40% of the test. This is just approximate. I did not write the test yet. Chapter 2, probably about the same, maybe about 40%. And chapter 3 would be about 20%. But those are just approximations. Most of what you want to be doing to get ready for the test is doing a lot of practice problems. So aside from that, you need to have a few basic things under your belt. There's not a lot of formulas to memorize. There's not a lot to memorize in general, really, in this class. But there are a few things that it would really just be good if you knew them cold. So I'm going to give you this list of sort of 10 good formulas. And these would be formulas that it'd be better to just know them so you don't have to derive them. So what I'm going to do tonight is I'm going to make this list of formulas. That's kind of going to be my introduction to the review, and then the rest of the review, basically the way I like to do my review sessions is to just start throwing problems at you, and then we'll just see how the questions go as we call them. And just interrupt me as much as you want. We have no real constraints here. We have plenty of time, so if anything's not clear or you need an elaboration on anything, just be sure to let me know. So, okay, so the first formula that everybody definitely needs to know is the formula for an integrating factor. Remind me again, when do we use integrating factors?
Like the first order linear.
Exactly, to solve a first order linear differential equation. That's in section 1.6 of the book. So here's the formula for it, e to the integral of p of x dx, where the p of x is the coefficient of the unknown function y. So the differential equation is y prime plus p of xy equals q of x. So this is a linear differential equation, and that's in section 1.6. And it is very important that the y prime be such that the coefficient is a 1. Okay, so if there were any coefficient in front of the y prime, you'd want to divide it through before you identify what p and q are. All right? So this integrating factor is how you convert this, or how you get the solution to the linear differential equation. So you have to know this integrating factor right here. That's a very important one. Okay, second one, related to it, if we go to the Bernoulli equation, and of course we want to know that one too. The Bernoulli equation is almost exactly the same. The The only difference is that on the right-hand side of the equation, you also have a power of the unknown function y. So y to the n power. And for that Bernoulli equation, you need to know the conversion, how to convert it. Remember that a Bernoulli equation through a change of variables becomes linear. And the change of variables, and no matter how many times I emphasize it, somebody always messes it up. So don't let it be you. U equals y to the 1 minus n is the formula for that. And if you make that change of variables, then it turns it into a linear differential equation, which is u prime plus 1 minus n times p of x times u equals 1 minus n times q of x. So this is the new equation that you get after you change variables. Okay, so I'm kind of cheating. I say there's 10 good formulas to know, but here's 3 right here, all in this one item. You sort of have to know all of that together. Okay, so far so good? All right, and then the third one is the homogeneous differential equations, or homogeneous of degree 0 as they're sometimes called. By the way, the Bernoulli equations, it's 1.8. Homogeneous differential equations are also in 1.8 in the book. So this one is just the substitution y equals x times v. And when you substitute that change of variables into the differential equation, you get something that becomes separable, right? New erasers tonight. Maybe these boards will stay clean for a while. So what happens is, so you plug in what y is, and then y prime is xv prime plus v. So these are the conversions that you use. And then what happens is the homogeneous equation becomes separable. So it becomes, there's not really a formula for that. I'll just say it becomes separable. Right. Okay, so separable equations are easy. You just algebraically put the two variables on opposite sides of the equal sign and integrate both sides. So that's kind of the trick to that. Okay, the fourth one is the differential equation applications. So there's sort of two parts to this one as well that you should know. The first one is the Newton's law of cooling, so I'll call it part A. So Newton's law of cooling, and that's the one that says that the rate of change of the temperature of an object with respect to the time is a negative proportionality constant times the quantity T minus T sub m, where T sub m is the temperature of the medium. So try not to confuse the differential equation with what its solution is. So if you actually separate the variables, remember this is a separable differential equation. You can put all of the little t's on one side and everything else on the other side. If you actually separate this, I don't think you need to write this one down necessarily, but we did derive the formula for the temperature. It looks like this. This expression here is not the differential equation. This is the solution to the differential equation. If I ask you what is the differential equation, it's going to be this. Okay? Brandon?
I thought I read in one of the review packs that if we get one of these problems, it'll give us this.
I don't think so.
What is a different one?
Yeah. Well, I say again?
I think it was the mixing problem. There was a note that you had.
Oh yeah, you're right. It's-
Oh, for the mixing problem.
yeah,
Okay.
that's what it was.
Right. So the mixing problem. This is the. I'll write it down. But yeah, this one's a little more complicated because there's so many different variables to it. But essentially, what it says is that the rate of change of the amount of a chemical in the tank at any given time plus R2A over V is equal to R1C1. This is the differential equation governing the mixing problems. And so that's one that is linear And I can give you this equation, you just have to know how to plug the numbers in. The R1, the C1, the R2, the V, to be able to identify those. And then, of course, you use integrating factors to solve it because this is a linear differential equation. So this is coming out of section 1.7 right here. Newton's law of cooling is really 1.4 because it's an application of separable differential equations. So a lot of chapter 1 is kind of getting covered here. By the way, the other thing to do is to, of course, not only go back and try and do the quiz again. The blank quizzes and the blank group works are still online. If you want, you can just print those out again. You solved them once already, the group works, with your group in class, but now would be a good time to go back and try and redo them on your own, see if you yourself have it fully down. And so you're going to see some good examples of all of these things in those group works too. So, okay, so those are the main formulas from chapter 1. Then I said I have 10 good formulas, so I'll try to go through the rest of these kind of quickly. The fifth one would just be the invertible matrix theorem. It would not be a bad idea to sort of know all of those statements that go with that. So again, this is in the very back cover of the book. This is the, A, B, C, D, E, F, G. We've done A through G so far. So later in the semester, we're going to be doing more of this, but for now, A through G would be what you'd want to know. Do you know what I'm talking about? So the first one is A is invertible, and the second one is, AX equals B has a unique solution for every B. Yada, yada, yada. There's a bunch of other formulas. The determinant of the matrix is not 0. That's another characterization. A is row equivalent to the identity. That's another example. The rank of the matrix is its full rank. So if it's an n by n matrix, then I'm going with n. The rank being the number of pivots. All right, I actually think I have that on my list here too. Yeah, I actually have that on my list here too. So the rank of a matrix is equal to the number of pivots. So stuff like that, so that's a good formula to know. So yeah, so things like that are good. So that's the invertible matrix theorem. The rank of the matrix is here. Then we have a couple of other things that are a little bit more recent. This is something definitely worth knowing. Just the formula for the inverse of a 2 by 2 matrix. It's good to just know that one cold so you don't have to do Gauss-Jordan elimination to solve it or something. Right? You can get this in a very short little calculation. Basically it's 1 over AD minus BC times the matrix that you get by swapping A and B and putting minus signs on B and C. So there's the formula, and of course, AD minus BC is just the determinant. So if the determinant is not 0, then you can actually compute that fraction. All right. More generally, the inverse of any matrix. We just learned this on Wednesday of last week at the end of class. I always worry about the stuff that kind of gets covered late. Because it takes time to soak it up. The homework that you're doing for tomorrow hopefully gets you on track for it, but please don't overlook this because this is very, very important. You basically take the adjoint of A, which is the transpose of the matrix of cofactors, so maybe I should put that as number 9. The adjoint of A is the matrix of cofactors transpose. So if I transpose the matrix of cofactors, I get the adjoint. If I then divide by the determinant, I get another nice formula for A inverse. Incidentally, if I ask you to find the inverse of a matrix, if I don't say anything more than that, I just say find the inverse of the matrix, then you have a choice. You can choose to use the Gauss-Jordan method from chapter 2, where you apply EROs to the matrix and you attach the identity matrix. You guys remember that? you're certainly welcome to do that. You can use the Gauss-Jordan method to find the inverse of the matrix, but you're also welcome to apply this method if you prefer. On the other hand, if I say something like use the adjoint method to find A inverse, then I want you to use that method. Okay, so you really do need to know them both. Okay, I don't want you just saying, well, I don't need to remember how the Gauss-Jordan method works because I've got the adjoint method. I might ask you, show me the Gauss-Jordan method, right? Because that's something that we learned. Okay, so anyway, so here's the adjoint of A, and then using it to find A inverse. And then my last formula here, my last formula is just the, number 10 is just the cofactor expansion. So everybody should know, and this one, almost I don't need to write it down because you don't really need the formula so much as you just need to remember the process. You have to take your matrix, the goal of cofactor expansion is to find the determinant of your matrix. And if you choose a row or a column, then you can expand that row or column to find the determinant. So we have these formulas for the determinant of the matrix. So the first one is if you go along the ith row, AI1 CI1 plus AI2 CI2 plus dot 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 dot. All right, or you can also expand columns. So A1J C1J plus A2J C2J plus dot 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 dot. Okay, so something like that. I said 10 formulas, maybe I should add one more, because I just thought of it, which is so let me add one more. So I'm going to make this, here. I'm just going to make this totally correct. 11 new formulas, okay. So one more, and what this one is just the Cramers Rule. Cramers Rule. So Cramers Rule just says that if you're solving AX equals B, then the formula for X is, well, it's just a vector of Xi's, or I'm going to call them X sub K's. So it's just a column of unknowns, and basically X sub K is the determinant of B sub K divided by the determinant of A. X sub K is the determinant of B sub K divided by the determinant of A. How many people know what I'm talking about when I say that? Okay. If you don't know what I'm talking about, it might be because it's on the video. So if you haven't had a chance to watch my literally it's less than 10 minutes on Cramers Rule, I basically just give you the formula for solving the system and do an example for you there. The Cramers Rule, it used to be a few years ago, I didn't teach it in 250B because, well, I just didn't have enough time. And then I started getting students telling me, oh, I need Cramers Rule over in my engineering classes, and so I realized it's probably a good idea if I show you guys how it works. So I started including it, but some of these review materials, see, I like to think I'm not too lazy, but sometimes I am. So these review materials, I wrote them up a long time ago, and so there's not a lot of Cramers Rule stuff on the review packet. So don't underestimate that. You may need to just do a little bit more supplementing of that on your own. It is in the homework that you're doing for tomorrow, so I'm hoping that that will help you out. And then if you didn't watch the video yet, that would be great because you'll get to see it there. And I do an example and everything. So those of you who did watch it, did it make sense? Sort of thing? Okay, good. All right, well that does feel like quite a bit, I guess. I thought, oh, this will go quick. But there's quite a few formulas here that you can see kind of all three chapters are represented, woven into this. Did you have a question?
Yeah, is the more to the property that determines like the determinant of A times the determinant of B?
Yeah, you need to know those things too, right? I didn't put them in this list because when I'm thinking of formulas, I'm thinking more of things that maybe you just, I mean, see, things like determinant of AB, you kind of just imagine what the formula should be, even if you didn't specifically memorize it. These are almost things that are so important and maybe not totally automatic to you that you should make flashcards and, you know, put them under your pillow at night or something, osmosis to get them to sink in, right? So yeah, I should be careful when I write these formulas. These are not the only formulas. There's a lot of other things too. But these are sort of the main ones, I guess. But yeah, properties of determinants, that's really important. How the EROs affect determinants. And again, as long as you follow through on reviewing the group works again, you're going to run across those problems again, which means you're going to be reminded that this is something you need to know how to do, and if you're stuck on it, then you know you need to put a little more into it to remember it again.
I had a question on one of those properties. You wrote down that the determinant of B plus the determinant of A does not equal to. Do we need to know what it equals to, or
there is no formula for it.
Okay.
There is nothing you could say that would be a formula.
Okay.
Basically, what I meant by that, so I'll just put it here really quickly. Determinant of A plus B, the thing people sometimes want to believe is that you could add the separate determinants. But the fact of the matter is you can't do that, but there is no right thing to say that it is equal to. It just depends on the matrices. You just have to take the problem given and figure it out. Yeah. This is a good little thing. By the way, I will probably ask you something theoretical on the test on Wednesday, where you're not really doing a lot of heavy calculations. I mean, of course, there's going to be the problems with the EROs, and there's going to be, doing some of these obviously very computational sort of calculus-like differential equations. But what will make this test probably feel a little different than just a raw calculus exam is that we're a little bit higher level here, where I'm now kind of expecting a bit of conceptual understanding. So asking you to give me an example of something that's not true wouldn't be out of the realm of possibility. Another example might be, we know that if A is invertible and B is invertible, then so is A times B. That's true, right? But what's not true is if A is invertible and B is invertible, then so is A plus B. Addition just doesn't work very well, right? It doesn't work well here. It also doesn't work well with inverses. I might say, give me an example of two matrices that are invertible, such that after you add them together, it's not invertible. Like that would be, maybe it's even on my sheet. Well, it's not on my sheet, but things like that are on my sheet. So those are the sorts of things that are good to just think about.
So you don't actually want us to create a matrix, right? You just want us to algebraically do a proof?
No, I would want you to give me an example. So if I say
okay.
give an example, just like here, as you'll see if you review the group work, a very specific example is all you have to give me. And usually with matrices, 2 by 2 examples are good. That's kind of the best size to work with, because with 2 by 2, of course, it's easy to find inverses of matrices just from the formula. You don't have to spend a lot of time calculating determinants and stuff. So 2 by 2 is a good size. Okay. Any other questions so far? We're doing okay. Let's do a little bit of practice. I have 7 practice problems here, and we'll do as many of them as you guys would like to see, and then if we're bored or whatever, we'll call it a day at any point. But let's just see what we can do with some of these. I'm not going to necessarily do them in order, though. I'm going to kind of jump around, just depending on how I feel. Okay, so here's the first one. The first problem that I want to go over is determine the 4-3 entry of A inverse, where A is this matrix right here. 2, 0, negative 1, 3, 0, 1, 0, negative 1, 0, negative 2, 1, 1, and 3, 1, 0, 0. Okay. Now you see see, this is a pretty big matrix. Like usually, 2 by 2 matrices is a little too small for most examples because you can't really test that much. 3 by 3 is kind of the optimal size. This is a little bit bigger than your normal problem, but there's a reason that I can get away with it here, which is I didn't ask you for the whole matrix. I only asked you to find one entry of it. So that actually will make things quite a bit easier. Okay, let's talk about that. Just erase the board first. Okay, so we're not being asked for the whole matrix A inverse, we're just being asked for one entry of it. So do people have any thoughts about how to move forward with this?
Find the binder or
Okay, so well, cofactor expansion finds determinants. We have two methods for finding the inverse of a matrix. One of them is the Gauss-Jordan method that we learned in Chapter 2, and the other one is the adjoint method that we learned in Chapter 3 that uses determinants. I guess my first question would be, which of those methods do you think would be better to use here? We're talking about finding an entry out of A inverse, so those are the two methods we know. Which one do you think would be better? The adjoint method is absolutely right. If you try and do the Gauss-Jordan method, of course, this is a big, huge matrix. You're going to have lots of EROs, probably get lots of fractions, right? So the adjoint method is good. And the other thing that's nice about the adjoint method is, remember, let's write down what the adjoint method is. It tells us that the A inverse is 1 over the determinant of A times the adjoint of A, but the adjoint of A is the transpose of the matrix of cofactors. So would you agree with me that the 4-3 entry of A inverse, how could we get that without having to calculate the whole A inverse? What do you suppose I would do?
Find the determinant of A and then find the 3-4 entry of the cofactor.
Exactly. Find the 3-4 cofactor and divide by the determinant of A. That's exactly right, because the 3-4 cofactor, whatever it is, becomes the 4-3 entry in this adjoint matrix. And you're basically going to take, see, how do you calculate A inverse here? You take every entry of the transpose of M sub C and just divide it by the determinant of A. So we need the determinant of this matrix, and then we need the 3-4 cofactor of this matrix. Let's do the determinant first. Is everybody with me? Okay, let's do the determinant of A first. How would you like me to find the determinant of this matrix? Okay, be careful. No. Okay, the arrow method only works for a 3 by 3 matrix, right? The arrow method where you do the diagonals this way and this way, that nice formula only works for 3 by 3. You cannot use it on, that's one reason why I made this a 4 by 4, was to force you to not use that method. So, anybody have another idea?
You can cofactor expand on the bottom row since it has 2 zeros and 1.
Yeah, the bottom row is a good choice. Any row or column is perfectly acceptable, but choosing a row or a column with a lot of zeros usually makes things easier. Okay, so I'm going to go with that. Let's do the bottom row, okay? So we're trying to find the determinant of this matrix, and we're going to expand along the bottom row. Now, remember that when we do that, we have this alternating plus minus thing that goes on. And if you think about, okay, so remember we had this little mnemonic. You always start with plus in the upper left corner. If you think about the 4-1 entry of a matrix, it's going to be coming with a minus sign. So I'm going to take this 3, which is the entry that I have here, but I know already that I have to change the sign because it's in an odd position of the matrix, basically. And then what do? I cross off that row and column. That leaves me with the 3 by 3 matrix right up there. It's a smaller matrix. And now